I now want to talk about the idea of geometric transformations. So consider a transformation that stretches a vector's x-coordinate by a factor of 2, but leaves the y-coordinate unchanged. So if we have a vector a, which is 1, 1, then it becomes a new vector, a twiddle, which is 2, 1. Or a vector b, which initially is 2, 1, becomes a new vector, b twiddle, which is 4, 1. Or c, which originally is 0, 2, well, it doesn't change. It becomes c twiddle, which is still just 0, 2. It doesn't do anything to the x vector at all. And so on. More generally, this transformation is going to transform an arbitrary vector. So it takes any arbitrary vector, let's say v, which is written as x, y, or an xy, into a new vector v twiddle, x twiddle, y twiddle. So how does it do that? What does it do to the components? Well, what we can do is we can write this as a matrix equation. It take the new vector x twiddle, y twiddle, in terms of the old vector xy, is you multiply that original vector xy by the matrix 2, 0, 0, 1. So v twiddle is mv. When we write it this way, we say M is a transformation matrix. It does a geometric transformation of our vector xy. So there's a number of common transformation matrices that we should just talk about and get out of the way. So one is just 1, 0, 0, 1, 1 along the diagonals. That's just the identity matrix. And of course, that does nothing to the vector. It doesn't transform a vector at all. There's another one, which is m 0, 1, 1, 0. And this matrix, if you think about it, multiply it out, it rotates vectors by 90 degrees in the counterclockwise direction. Again, you can multiply that out and confirm that if you want to. Another matrix, which is cosine alpha minus sine alpha, cosine alpha, that also rotates vectors, it turns out, and it rotates them by an angle alpha in the counterclockwise direction. Another common matrix is -1, 0, 0, 1, and this transformation matrix reflects vectors across the y-axis. So it just takes the x-coordinate and turns it into negative x-coordinate. So it's reflecting across the y-axis. One thing to be careful of and to note is that it matters the order you do geometric transformations. So geometric transformations are not commutative. You can't change their order. So in particular, let's consider an example. So I start with a vector v pointing along the x-axis here. And now I'm going to reflect it across the y-axis. So I reflect across the y-axis, so now it points in the negative x direction. And then I'm going to rotate it 90 degrees in the counterclockwise direction. And so then it becomes a vector which points straight down. Well, let's say I switch the order. So let's first I rotate by 90 degrees in a counterclockwise direction. So now the vector that I started with becomes one that points up. And then I reflect the vector across the y-axis. Well, if I reflect this vector across the y-axis, it doesn't do anything. It's still pointing straight up. Notice that these two results are not the same. It matters the order that I do the geometric transformations. Mathematically, this means if I do my reflection matrix and then my rotation matrix, that is different than doing my rotation matrix and then my reflection matrix. So the order of this multiplication matters. And you can multiply these two matrices out on both lines, and indeed you'll find that they are not equal. So do be careful on what order you're doing your geometric transformations, because it does matter. All right, let's say I give you a random matrix. So M, in this case, let's just look at this matrix, 3 halves, 1 half, 1 half, 3 halves. What does this do? What does this matrix do as a geometric transformation? In general, it's really difficult to say what a matrix does just staring at the matrix. So in general, we're going to have to do a little bit of work, and the work we're going to need to do is to find the eigenvalues and the eigenvectors of the matrix. So I went and found the eigenvalues and eigenvectors of this matrix. One of the eigenvalues is 1 with eigenvector 1, negative 1. The other eigenvalue is 2 with eigenvector 1, 1. So I can get some interpretation in this case. So m times v2 gives me 2 times v2. So if I had a vector v2 originally, then I multiply the matrix m and it stretches that vector by a factor of 2. So any vector which is along or it stretches any vectors along the line y equal to x, and it stretches them by an amount of 2. The other eigenvalue and eigenvector, mv1, leaves v1 unchanged. So that tells me that it keeps the perpendicular direction to v2, it keeps perpendicular direction to y equal to x unchanged. So this matrix, all it does is it stretches vectors along the line y equal to x. So let's look at an example of applying that to the vector a, which is 2, 1. So a tilde vector, the new vector, is now m times a, which is 7 halves and 5 halves. So in pictures, I've got my line y equal to x here. My original vector a, say, points up like this. And then I multiply by m to get my new vector a twiddle, and it's going to stretch by a factor of 2 along the line y equal to x. That's what my matrix M is going to do. Okay, so this idea of geometric transformations is not just for vectors. In particular, you can use them on things called point matrices. So let's talk a little bit about what a point matrix is. So let's draw a xy plane here and mark off some lengths here. So I want you to consider the matrix P, which is 0, 0, 3, 0, 3, 2, 0, 2, 0, 0. So this, it turns out, this point matrix describes a polygon. So this first column tells me draw a point at 0, 0, then draw a point at 3, 0, and connect a line. Then draw another point at 3, 2, and connect a line. Draw another point at 0, 2, and connect a line. Draw another point back at 0, 0, and connect a line. So this describes a polygon P. So now let's imagine taking, say, the rotation matrix that rotates by 90 degrees in the counterclockwise direction, and multiplying that by P. So I take my rotation matrix and I multiply that into P. So with a vector, this would rotate by 90 degrees in the counterclockwise direction. So let's see what we get multiplying this out. You can check this if you want. So this says now draw a new polygon starting at 0, 0, a new point at 0, 3, draw a line, a new point at negative 2, 3, draw a line, a new point at negative 2, 0, draw a line, and then another point back at 0, 0, and draw a line. So I get a new polygon here, which is m times p. And indeed, this is exactly a rotation by 90 degrees about the origin. So this idea of point matrices and geometric transformations can be used for computer graphics, for instance. If you want to draw polygons and then move them around and rotate them, you can use geometric transformations to do that.